Hello everyone, and welcome to this new video dedicated to INDUX-R use case 5, Sport Immersion. Today, we will present the progress we have made with the embedded equipment inside the racing cars. Our first goal was to develop the technology needed to acquire data during field tests. We have many onboard sensors that must work together and be synchronized to ensure consistent results along the entire media chain, right up to the end user. A key component is our multiplex. To gather and transport all data streams reliably, we embed them in an MPEG-2 transport stream. At present, we carry 5 channels, perfectly synchronized from acquisition to delivery, and expandable as needed. Let's start with audio. An ambisonic microphone has been integrated into the NOMADE car system. It captures spatial sound for reproduction in the XR headset. Each of its 4 capsules is acquired independently, then compressed with a dedicated spatial compression method that improves efficiency without reducing quality. This stream is then inserted into the multiplex. Ambisonic audio reproduces the car environment, the roar of the engine, the wind, tire screeches, and braking. To improve speech clarity, we also added a second mono microphone on the co-pilot's helmet, though it could be on the driver's. This channel focuses on intelligibility, and its volume can be adjusted separately for optimal clarity. Now, for video. NOMADE car was initially designed for GigaVision, IP or USB cameras, often GoPros in motorsport. However, action cams are not optimized for low latency, one of our key constraints. With them, the out-of-camera delay was never below 500 milliseconds. We therefore turned to GMSL cameras, designed for embedded systems, and reduced latency to just 60 milliseconds. For immersion, XR requires 360 degrees video. We tested several cameras and developed the full pipeline to manage them. To achieve the expected quality, these systems demand 8K definition and about 10 megabits per second. This too is integrated into our multiplex. Yet latency remains an obstacle. 360 degrees cameras have at least 500 milliseconds of delay, which is acceptable for replays but unusable for coaching or remote driving. For now, we prioritize low latency 2D views and use 360 degrees only where delay is less critical. Metadata further enriches the experience. We already embed GPS and IMU data. The IMU drives a 6 degrees of freedom platform to reproduce car movements, while GPS will provide a live map of the track. To minimize bandwidth use, we apply KLV compression before inserting these into the multiplex. Next steps include retrieving data from the car's internal buses, tire pressure and temperature, steering wheel angle, brake and throttle position, driver biometrics such as heart rate to indicate We carried out 2 major field acquisitions to gather data now being shared with the consortium. Low latency remains our main challenge, and to address this we are building a lab benchmark, the subject of our next video.